secret answer, which was in the previous, this is back a while ago that we did this, but if you bisect this angle, you're done. Yeah. But then the cycloids are quite...
that was rough.
Yeah. You pay a lot for getting perfection, right? I mean, the V gets you there pretty quick.
That took me
You pay
probably
a whole
minute.
bunch of money to make that extra root there that's perfect.
Yeah.
They're pretty close too.
I think each one of the constructions took me about 30 minutes by hand, but the cycloid took about 28 minutes of that, and then the V was just like, oh, angle and there we go, done.
Yeah, yeah.
Can I redo the part B and give it to you?
Yeah.
I just realized my B would be
Yeah.
wrong.
Go ahead. Right.
I'll redo it.
I think this is extra because it's on my table.
Yeah,
I
so
already
we
have
can
it.
return
I think this is extra.
Huh?
Did everybody get a unit 4 printed copy?
Yeah. I have it on my
This is from the last set. Okay.
This is weird.
Exactly knew that. It's like,
You did?
it worked out really well for some of them, and then not for any of them. Is what you're saying.
But during the winter time, I'll try my best to keep it on as much as I can. I dropped her off in the morning, so then I picked her up. Because I usually go to school at 9 before, and then I drop her off as well.
Okay, the resonance behavior of the classical Lorentz response function, or Green's function, is something that I want you to really appreciate. So there will be future problems that involve the detailed algebra of this amazing function. And we got to the point where we were just looking at the resonance behavior, resonance amplification, and the beginning to understand the quality factor that represents the factor of amplification that you get as you approach resonance. Now, the steady state solutions, the complete solution, the transient solutions versus the steady state, is something also I want to talk about today. Now, this classical oscillator response is based on inverting, that is what a Green's function really is a quasi-inverse of the operator. It's based on an operator that's Newtonian, that is, it's a differential equation of second order. Now, one of the things I want to show in this whole section on resonance is that we're very close. In fact, I'll be showing you plots of this Lorentz function that are really close when it's a high quality oscillator to the quantum Green's function for the Schrodinger equation. And the Schrodinger equation, as you know, is first order differential equation in time. Okay? So when you invert that one, you get a very simple 1 over z. And 1 over z was a function we talked about a lot in unit 1, chapter 10, when we did the complex variables. So I want to show you the geometry of that function, 1 over z, in the high quality oscillators for the classical thing, but also when you make it really clean, then it becomes virtually identical in the resonant region to the propagator that you're going to be using if you do some field theory with quantum oscillators, electromagnetism, quantum electrodynamics, all that kind of stuff. So that's one thing I want to try to get across in the second half of this lecture. And depending on what time we have, I would like also to go on to lecture 21, which really have been scheduled for today, and look at the case where we have two oscillators that are coupled. So instead of driving one oscillator with a force that is basically infinite compared to anything the oscillator can do, there'll be two driving each other. So what we learned from looking at the phase behavior of the case in which the driver is, shall we say, omniscient or omnipotent, I guess. It just sits there and drives the oscillator, and the oscillator can respond whatever the Green's function lets it do. We'll be looking at a situation where when the one oscillator gains energy, the other one loses it. In this case, we're not tracking the energy that the force puts in to these force damp, this whole force damp harmonic oscillator. So I'm going to rush ahead here on these things that we've already done when we were developing just the equation of motion without any force. That was this part right here, in which you get a damped oscillator that in our case, when we had a gamma of 0.2, that was the value that we picked for the frictional damping force, and with a gamma of 0.2, the lifetime, the 95%, or shall we say decay to 5% lifetime, was 3 over gamma, and that's 3 over 0.2, 3 over 1/5, that's 15. That 3 over gamma is the 5%, to 5% lifetime. And having that that value, that is that, shall we say, benchmark or figure of merit is, I think, a really important thing. So the time 5%, 3 over gamma, 15, that's what we're dealing with, and we'll be dealing with this oscillator. It has a gamma of 0.2, and we'll be studying what happens when it gets stimulated with frequencies that are around. We took it up to the resonant frequency. We still have to go beyond and look at that. But let's just get the algebra and the mnemonics, the numbers, the figures of merit down. Remember, I said that if you want, you can do better than just writing e to the -3 is 5%. You could write e to the minus pi, which is 4.321%. Okay, now you have four-figure estimation of decay, or later on uncertainty, all that sort of stuff. And it's a little bit of a game here where when we talk about uncertainty and then use tremendous precision to describe something that's imprecise, becomes sort of a joke. But in the high resolution business, high resolution means you really are tracking everything. And so this becomes useful. Okay. Now, the other thing that I want to point out is the number of oscillations, the number of heartbeats that an oscillator has before it has bankrupted itself. Well, if you're given that time and then you just multiply by the frequency that the oscillator is operating at, and have here the 3 cancel the pi, that's if we're going to use this thing, but remember we could have used the pi and then it would be not an approximately equal sign there. But in any case, the idea of the frequency, be it omega gamma or omega 0, which is what we'll usually say, because if you remember how close omega 0 is to omega gamma for gamma values that are in the neighborhood that give you, you know, lots of heartbeats before the thing dies. So, as I say here, we could do it very precisely, but let's just stick with the this particular 2-figure accuracy. That'll be good enough for what we do today. Okay, now, are there any questions about this? I'm going to make sure that this much of the what we did last time is in the forefront of your minds as we study resonance one more time here in the neighborhood of the natural frequency. So we're bringing the, whatever it is, a laser or a microwave, something or other, up to the natural frequency, omega 0 of some molecule, atom, whatever. That's pretty much what we do in spectroscopy. But there are very sophisticated experiments coming online where we do things to the atom or molecule or solid that change its natural frequency and bring it into tune with some laser, just the opposite, right? And if you're, you know, used to be you had to tune your radio to hear the AM stations, right? You're tuning that oscillator there so that it gets synced up with a frequency that you can't change. So it can work both ways. Those 2 frequencies are the one that you call the stimulus and the one that you call the natural, or the gamma, if you're being very precise, frequency are at play here. Okay, so I'm going to go ahead on both of these things to the part where we talk about the inverse of the Newtonian equation of motion here. That is, this is the Green's function. I just flipped the differential equation over, so to speak, but only for a particular frequency that we're interested in. The stimulus frequency, omega s, is there. And that is the Green's function. There's Mr. Green again. And there's a sort of an engineer's block diagram of a stimulus coming in, and then the Green's function acting on it by multiplying it and giving us a response. So it's that response that we're doing the algebra for again today. So here's the algebra that gave what we looked at last time. And the key number, the really key number when you're doing very careful a sort of high resolution oscillatory phenomena is the phase angle, the phase lag. That is your response here with its amplitude. That's the magnitude of this Green's function, this modulus of the Green's function here, the absolute value, if you will, of this Green's function, which is that real number, okay? And then this is the polar form here, the radial amount of the stimulus here, and then the phase lag of the response. You see, this length right here would be that number, and then this here, the phase length, be behind, usually behind, but we're going to see that it can get ahead too. That's a very important piece of physics right there as we go past resonance. But when you're in low resonance with your stimulus, you're going to have some sort of angle, usually very small, but as you approach resonance, this angle is going to swing up 90 degrees. That's going to be what it is at a perfect resonance. And then as we go past that, as we will shortly here, we'll see it keep on swinging until it's completely out of phase. And that's what happens when you overstimulate, so to speak, running a frequency higher than the natural frequency. Okay, so is that clear so far? What is about to happen here? Okay, and then this is the function done very carefully as opposed to the pixelated examples that most of this particular lecture has. But we're going to run this and this fairly carefully today. So we'll have TC help us get through the various pitfalls that can happen when we drive this particular function. So this is going to be interesting in making sure that we understand just how this full wave and half maximum, the FW, well, I have all kinds of acronyms that need to be brought in here. Let's see if there's anything else I also have to mention. When the frequency is within gamma, plus or minus, that's this little region right here. Remember, it's 0.2. Gamma is for things that we showed later on here. This particular gamma is 0.15, so it's a little less, and this is a little bit higher quality oscillator than the one that's with 0.2. The smaller you can get the gamma, that is, the tighter that you can get this. Basically, the area of this thing is sort of constant. As you squeeze on this, as you make the uncertainty for this thing smaller and smaller, this takes off like a great skyscraper. We approach just a naked atoms response. We're talking about a omega over, omega over 2 gamma amplitude ratio, the ratio of this to this, not just 15, but 150,000. So the range of numbers that are available now in time and per time measurements that, as I've said, skyrocketed. Okay, so this is the old picture with all the pixels showing, and this is our favorite 0.2 gamma right here. You see it's a little bit narrower than the other picture, and the full wave half maximum. Okay, we're talking about here the full width half maximum. That is, you go to half the height of your actual resonance, and that's where the real part of the response takes a turn and heads yonder down to here, turning around at the other side of the full width half maximum. So this is half maximum in this direction. We're located right about rho equal 45. Would actually be about there for this particular thing, as is shown more precisely in that picture over there. The resonance region here is just a little bit here above 0.5, and that's arbitrary units, so I'm not making a fuss about that right now. But this, you can see that the other side of this thing, that is, when you swept through the resonance region and are now on the downside here, where your phase velocity is faster than light. If you're looking at an optical phenomenon here, this one is slower than light. It makes a big change right there as far as the optics and wave dynamics goes. But that's what we're talking about right here, is the full width of this imaginary part, and it is very close to half of the maximum. Now, when I say things are very close and sort of perfect, it's the quantum oscillator, the thing that will come later, the kind of thing that you're used to when you say Lorentzian. Lorentzian usually refers to 1 over not quadratic frequencies, but linear frequencies. And when we get to that, all of these things I'm saying about this thing that are nearly true are exactly true for that, as we'll prove. But I'm going to give you a problem to find out where is the maximum of this function, and it isn't quite at omega minus gamma, or the minimum of this one isn't quite at the omega plus gamma. Not quite. There's just a little bit of shift there. I think is going to 0 as we approach a gamma very small. Okay. Let's see if there's anything else neat to say. So our number of heartbeats that the 15 that we get is the ratio here of this to that. What you get at DC, what you get when you're right on omega 0. Not right on omega gamma, on omega 0. That would be what you would be looking for there. And we want this thing here, omega s squared, to match omega 0. This is not omega gamma. Okay? All right. Well, if there's anything else I can think of, we can go on, and I think it's time to show some of the actual dynamics of this. But in order to do that, as we pointed out last time, in order to simulate this thing, we got to put it up with this guy. We start this thing with a particular initial conditions. Let's say we started with initial conditions cold oscillator. That is, start with a cold oscillator. You got a cold atom, okay, and you come in with your laser at this frequency. Well, the initial conditions are this is 0, but at the stimulus frequency, this is anything but 0. This is, you know, a huge skyscraper, maybe 105,000 times the DC response you're getting as you approach with your omega s to omega 0. Okay, so this is anything but 0, and there's nothing you can do about changing that. That doesn't march to your initial conditions. What you're going to have to do is have something here that is equal to this in huge magnitude with a minus sign. In other words, you're going to have to set this A here to something really hugely minus to cancel this thing, to make 0 for an instant, right? And then this thing is going to die out. So that's why it's called the transient by engineers and physicists, or essentially engineers as they're playing with this stuff. It's also known as a homogeneous solution. Remember that. That means no force in space and time. And you get this solution. And the main thing is that this thing lets you set the initial values to whatever you want to specify. And then this guy, the thing that is working on the inhomogeneity, that's what they call a function sitting on the right-hand side of an F equal ma equation, the force. This is not a function of initial values, but it pays attention to the stimulus, its amplitude, and its frequency is its parameters. Okay, so with the sum of this transient response, or else call this the decaying solution, and this the steady state, that's what we'll be simulating as we were just at the end of the lecture last time. Okay? And I think we took ourselves from the DC example up to one that was close to resonance here with the gamma equal to 0.2, so that the time of 15 seconds, that's the lifetime of the transient. After that, we're getting this and nothing else. So it takes a while for this thing to wake up and be a resonant citizen, as it were. Now I got to bring this guy forward as well here, so that we can do simulations on both of these critters. Now this is the, I think we look at this one. The thing that I want to go ahead and look at right now is when you have your stimulus not below resonance, not on resonance, but what happens when you pass the resonance with your stimulus and are above more heartbeats than the oscillator has. So I'm going to go ahead, since this one has stuff at the bottom there, I think I could use it to drive the, so there's just a basic oscillator. Now what I'm going to do is I'm just going to go here to controls and scenarios, and eventually we'll fix it so this sort of stuff is more available. But right now I'm going to look at, we looked at the forced damped oscillator on resonance. I'm going to move just above resonance with this particular setup. So here comes the force, and you can see the stimulus is being left behind. Okay, quite a bit behind, but it's kind of changing its amplitude also. It's being resonant, but then it gets to a certain point where it starts to come down a little bit. And so we're looking at just passing a beat between the transient and the responding Green's function, Lorentz Green response, okay? And right now, it's almost 180 degrees out. And that's not where it's going to end up. 180 degrees out would be a pi phase lag. That would be 3.14 or near that, okay? And we have a difference in frequency between the stimulus, omega 6.9, and roughly 6.3. So we're about off by 0.6, half of a hertz, okay? And you're seeing that as the beat frequency. And now we're approaching our 5% point there. And you can see that at this point, the oscillate from this point on, the oscillations of the transient will be less than 5%, decaying to really less than 5%. And by the time it gets to the edge of the screen there, it looks like it's you know, getting to the point where it's only about 20 or 30 pixels of amplitude in the thing. So now, from here on out, this is not going to change except to rotate. Is that we're really within this much of the steady state solution. Okay. All right, so
it's not truly a steady state, right? So the circle is going to go smaller and smaller by bit.
what is going smaller and smaller is that e to the minus gamma t, okay, of the transient. See, which would be added to this thing. And because it's essentially dead now, if I plot the thing with a little bigger time scale there, you would see that it's just steady. This thing has just stopped right on that particular circle, and that's where it's going to be. It's right in the center of this dark region. Okay. So when I get to, if I've come down by 5%, I mean to 5% after 15 seconds, after 30 seconds, right? It's 5% of 5%. right? It's essentially 0 for the plot here. Okay, and then as you know how the exponential works, it just keeps tacking on another 95% drop, right, of what you had before. Okay, so now what I'd like, of course, to do is carry this a little bit further, and let's see if I'll get the controls and scenarios there real quick. And I want to take this thing to the ultimate loop here. Let me go ahead and get this started here. This is considerably above the resonance, so let's just try that one out for a while here. Now you can see what I need to get this thing to the right initial conditions. Its response at this particular thing is about that big, so I had to have negative that in order to start out at 0. Okay, so there's the transient behavior there, and this is a beat that comes from rather quickly now because I'm located, I'm seeing here a frequency here of 7.5 compared to 6.2. That's quite a difference. So the difference is the frequency of the beat. So that's quicker now, but it's also lower amplitude. And what we're going to end up now is almost 3 for our final phase lag, and we're pretty close to that right now. You see that you're not going to see much of that snowplow passing behavior for something this far from our natural frequency of 6.28, or our omega gamma of 6.2800. The 6.82832 is 2 pi. This is 2 pi in that Pythagorean relationship for omega gamma. So we're approaching 15 seconds. We are now seeing a transient that is 5% of what we started with, which is as big as the total response is going to be in order to start at cold initial conditions. Does that make sense? Okay. Now, one of the things that you should notice, and I'd like to do that, I'll let that one just run for a while because it's pretty well. You can see this dark region right here. And you can see a little bit of a bend. It's not quite 180 degrees, not quite pi out. It's only 3 out, not 3.14. So that's a situation where if I go any further into the high frequency region, and we can do that, we might as well do it, what the heck. You only live once, or I should say you only die once. Isn't there a movie called that? With James Bond in it? Something like that. Anyway, I'm going to go ahead here and do where you're really above resonance. And what you're going to see here, remember we have a DC response, it's about this big. We're out here now at a frequency of 12.5, so our beats are just really fast. And we're going to end up with a row that's 3.1 now, essentially 3.99, 3.099, okay? So we're really close to pi, but whenever you do that, well, I think it's really hard to see what we've got here, but this kinkly thing with these fast beats is settling down, and by 15 you'll have a pretty reasonable sine wave, but it's going to be a really small one. Okay, it's going to be, about as big as the transient was when we started. Okay, it's working its way to that point.
What we need is a real-time readout of the row to show how it swings back and forth for
Yeah.
near that area.
Well, I think that the plot of the Smith cycle, okay, is good for that. It might be nice to have that, you know, actually sitting on the screen for the animations. You're definitely right there. Okay, it's 15 seconds, doing. That's the 5% lifetime, and it's now the beats are about the thickness of the plot here.
It's a
Plot line,
handled
okay.
sign.
And what you're seeing is really tiny response. You see, and this is only, you know, 6 or so hertz away. Okay. What we're talking about with X-rays is many times away and above the natural frequency. And for that, you get no response at all. That's how you get invisible. You're invisible to that frequency. Light just goes right through you. You're not there. Nothing there to respond. Okay? Unless you put something in there that's got a heavy nucleus with some really fast electrons. Electrons that can respond to a high frequency like an X-ray. Then you see it, right? And that's what X-ray of a human being is all about. You see the calcium, the heavier elements, they'll show up. If you happen to have a gun in your possession, it's not hidden anymore, you'll see that, because it's got lots of heavy metal, right? If you have any bullets in there, they really show up. Lead, okay? There's black on an X-ray unless you run at frequencies really high, which of course they don't. So that's getting into the gamma region. Okay? So that's some, you know, real physics to be aware of. When I say resonance is the single most important part of a phenomena of physics, I think you begin to see it mean that. It really means business. We are a bunch of waves, and we get used to it. Okay, so I think that pretty well takes care of it. Now, I can spend some time, rather than I think now that we have the scenarios in the canned version here, you can study some of these cases. This is where I turn the gamma way down, really make it small. This is gamma equal 0.2 that we looked at over here, and now I've got it down to essentially 0.001 or something like that. Now, you have to watch out. If you set it absolutely to 0, you're in big trouble, because immediately then you're dealing with a response function that goes to infinity. Okay, so that's why we don't take our numerical stuff. There's ways. I think we've got to sort of protect it so as you approach 0. It still isn't 0, so it won't blow up on you. But in any case, here I'm talking about resonance, and what I'm talking about is a straight line. This thing just builds an Archimedean spiral, a linear increase each time, getting the DC response quantity added to the radius of the circle that you're building bigger and bigger. Each time you get another DC, another DC, another DC, another DC, and you get a linear growth in the amplitude. That's the best a linear oscillator can do, you see. Now we're going to study a case where you drive it not from the right-hand side of the equation, but by having the oscillating force multiplying the dependent variable. When you do that, you can get an explosive motion, and that's what the trebuchet is all about, is a amplitude product. And you've got to realize that that's the thing that makes quantum mechanics hard, because the driving thing, the potential here, V of x, multiplies the dependent variable. We don't put anything on the other side of the Schrodinger equation. We put 0 there, right? Your stuff, it's an inside job. You're multiplying the wave function with something that wiggles or does whatever you want, okay? That's called parametric amplification, because usually when we talk about oscillators, the parameter for the oscillator, the kx squared, right, 1/2 kx squared, right, that parameter, you start wiggling that. That's parametric amplification, or parametric resonance. Okay, that's a whole chapter in this, which we'll hit eventually. But you can expect squirrely behavior there. You can expect tremendous explosive resonances that then are damped out explosively as well. Basically, it's chaotic quite often. So the way to really understand the trebuchet is through that kind of resonance. But let's continue our discussion of this while we're at it. Okay, so remember, and this is the thing that's actually done graphically, is you can exhibit the phasor for the steady state response, which in this case is 180 degrees out. Here it's just pretty close to the force. It's sitting right on top of it, in fact. You see, here it's pi out of phase with the response, and it's the sum of those two, the transient behavior plus the steady state response, gives you where the thing is right at the moment. So the little force triangle here for the resonant plane. Okay, and that's something worth talking about, but I'm not going to spend a whole bunch of time on that right now. That's some funny little geometric details that I don't think we need to worry about. Here's some more pictures of that. So be aware that when you're at resonance, and this is for very high quality force damped harmonic oscillators, so we're talking about gamma values here at 0.00 something. What you're talking about is the steady state response, always attached by an angle rho to the force. And when it's at 90 degrees, when the steady state response is at 90 degrees, that's when you're getting the most for your money. Because basically what's happening is you're fixing it. Well, maybe I should actually show it in action to make this point. Let me see if I can bring that up here. I think I will actually go ahead and get it going on this screen and pick resonance one more time just to make the point. Because this is where the complex variables stuff really helps us to tackle this thing. So we'll once again do the on-resonant case just to get an idea about that. But you see, what really happens is in that particular case, the transient wants to take this thing some other phase lag than 1.57, that's pi over 2, okay? But after a while, it just settles in. This is something that happens automatically. It just settles in so that the force is just exactly in the direction to drag this thing around the phasor circle, okay? Or the other way to think about it is the force is maximum just as it's passing the origin. Minimum just as it's going down past the origin. Maximum, again, you see, it's sort of, come on, baby, giving you the force right as you're passing, and then come on up, baby, you see. It's a dance. That's the dancers learn to, get their phase right in order to perform. Okay? So bingo, right there. That's being pi over 2 out of phase. That's what it means, is to have the force in phase with the velocity. And remember, the velocity is pi over 2 out, right, when we were doing our very first phasor analysis, okay? So having the product of FV be maximum, right, that's work, right, force times velocity. Okay, so it's simple sophomore physics that's happening here. And it just happens all the way until finally, because the thing is going so fast that the frictional forces are dominating, and if you sum that into this equation here, you would be canceling that one essentially to 0. Okay, so here we are at 15, already past 15, and the tops of this thing has leveled off. You can't see it here, but you can sure see it here. Okay, that's what we just ended the last lecture with, was approaching that steady state limit at resonance. Okay?
If you choose the next scenario up, we might be able to toggle the steady state plot, steady state transient plot, so that it's superimposed.
Oh,
Try looking in the controls for that.
Okay.
It's a new feature.
let's go ahead and try that.
And you can ramp her up, overshoot the resonance a
Go
little,
ahead.
and then
Pause
we
it.
could see how
Let me.
the transient
You're talking
adjusts.
about this guy here.
Yeah, next one down. Well, you were.
That's a linear ramp. We'll get to that later.
Well, you had the on resonance one down from that.
This one.
Well, okay, I mean higher frequency.
Oh, you want to go this way?
Yeah.
Okay, so we're above resonance. We're going to have something with the two guys like that, right? Okay, let's go ahead and do that.
Okay, now we might have to interrupt it and go back and reset it.
Okay, I'll do the resetting with this,
Scroll down.
and we'll turn on.
Transients. You're very close. One up. One up.
There,
Yeah.
right. Plot steady state transient phasors. And this is something
Correct.
I put in very early on when we first did those Macintosh things. But
It
here
is
you
present
can
in
see
the
it, whereas
classic.
there the pixels are so fat you can't see it. So let's just go ahead and reset for that. That should do it, right?
That's right.
I guess maybe we do start, right? Okay, here we go. Okay, there they are. Yeah, this shows it pretty well.
Okay.
There's the actual transient, okay, doing its wiggly stuff. It's got a pretty big amplitude, but now on the next go here, it's even more, okay? Now, meanwhile, the steady state, you can see where this thing's going to end up, where this Z is going to end up, okay? As the transient here, okay, now the Z is actually getting a little behind there. It's going to drag it down in amplitude. So here's the actual solution, Z, which is a sum. This is just literally a moving force parallelogram, okay, summing the transient and the steady state. Steady state just maintains its rho value of 2.8, which is a little more than pi, a little more than pi over 2, I should say. And as we're approaching 15, the transient is not so big anymore. Okay, see it right there. So the Z is closing in, the actual Z value is closing in on Z steady state as this thing dies. So you can hardly see the parallelogram anymore there, right? That's a pretty good thing. Just getting to 5% now, okay? But already you can see how it's working. So from now on, the steady state will just go on this circle roughly there. And it's daily business forever after that. Okay. All right, let's I'm going to pause these because there's some things we want to look at that involve the actual function of the thing. And of course some other details about that function that I want to try to make clear here. And so I'm going to pause this guy too. And I'll bring both of these back to the, skip by it there, back to the lecture notes. And there's looking at beats. But this is where I need to bring both of these things to look. Figures of merit again. Okay. Amplification factor, omega 0 over 2 gamma. Okay. The angular quality factor. Now there's the usual quality factor, the standard quality factor. I've never seen this guy in any text. I mean, it really helps to have that. So what we're already saying is that the 5% lifetime, we've already talked about that, is this thing. It's also the amplification factor. Okay. It's also, well, I say heartbeat count. It's also energy decay. If you look at this thing, relative amount of energy lost per cycle when you have something that's going down, E minus 2 gamma, okay? Well, that's very close to 2 pi over Q, okay? This is the definition of the standard quality factor. It's 1 over the change in energy ratio to energy itself. Now energy, you see, is a square of the amplitude. So we get a 2 gamma right here, and then divided by the frequency, that's 1 over the big Q. That's 2 pi times 1 over our angular guide. Okay, so the standard quality factor is just 2 pi of multiplying the angular one. Just like nu is multiplied by 2 pi to give omega, or omega is divided by 2 pi in order to give nu, the real Hertzian frequency as compared to the angular frequency. Well, this is involving amplitudes now going up and down. That's curious. We went through that a little fast there. How did we get, you know, this 2 gamma over nu 0, which is what they want, and that's what you need is 2 gamma thing. And then up here, you don't have that 2. You have this, you know, 2 sitting right there. Okay, that's, I think that's neat. It just works out that way, with pi nearly equal to 3. Okay, now, this is the uncertainty. What makes a wave uncertain? And that is when you don't quite know what the frequency is. You're listening to it, you're listening to the beats, but the trouble with those beats is they die out. You see, if this gets too big here in the denominator, and then this becomes less than 3 over gamma, which is kind of that thing that we use to characterize the tau 5% lifetime. Okay, when you get to that point, there's no signal left. Okay. Now, musicians that play guitar or other strings instruments where you adjust tune them by strengthening, tightening the strings. On a guitar, you push the 2 on the 5th fret, the 2 top ones, and compare the top one without being pushed, and then the one below it, which is up an octave, or not an octave, but enough so that when I hit the 5th fret with it, I get supposed to be the same frequency. But if I stroke that and it goes wah wah wah, then and that's a say a 1 hertz or a 2 hertz wah wah. That means I'm 2 hertz out. Okay, that's just a direct measurement of the beat frequency. This guy. But you can only, you know, for back being a physicist, you know, that just getting that within 1 or a fraction of a hertz, it goes whoa, and dies off. You're close enough for folk music, right? So that's what we're talking about here, is when you make your delta omega big, then you're not going to, you know, you're not going to be able to measure the frequency very accurately. So this boils down to a relationship which is just the product of the amount of time you've got during the lifetime, the gamma is going to affect you there, okay, and make that thing smaller as you have higher gamma, and your delta nu, the product of those two, is 3 over pi. Well, when that's close to 1, that's pretty much the uncertainty relation for a classical oscillator. Okay, you can get fancy here, right? Be very precise about imprecision, but right now for what we're doing, that's good enough. So the T5% 3 over gamma is what's, making this thing happen. Okay, so that's another another use for the angular quality factor. Okay. Now, it's also delta nu over nu, delta omega over omega. It doesn't matter whether you use the real frequency or the angular frequency. That ratio is still 1 over q. It's 2 gamma over omega 0, the inverse of the q. Make sense? I think these are benchmarks that can be used. Okay, now we're going for high quality, really high quality oscillator. Okay, I'm going to have such a high quality one that I can essentially assume that omega s is in the neighborhood, very close to the neighborhood of omega 0. That is compared to the gamma. And I want a small gamma in order to do this, otherwise it isn't going to work so well. But the basic idea is we take the omega s here, we just see this thing right here as a 2 omega s. So I take a 2 omega s out of this thing. Now this thing here is omega 0 minus omega s times omega 0 plus omega s, and I just treat the del omega 0 minus omega s as the variable that's important here, and throw the other part, the omega 0 plus omega s, is just 2 omega s. So I multiply by that factor right there, and then I have it in linear form. This is the quantum propagator for a quantum oscillator. It has this natural frequency of omega 0, and we're now having it coupled with some sort of stimulus. Okay? So that's one way to do this thing. Just divide by the natural frequency. If you're not going to change the natural frequency, this really makes sense to do it. So this will be what most people call the Lorentzian. The other thing, the Green's Lorentzian, is more complicated. So this is going to be a detuning here, delta. Okay, that's the difference between the omega 0 and omega s. If omega 0 is still greater than omega s, we're coming in from the low side. This is positive, but it can be negative. Okay, and it's just 1 over a complex number z. Okay, and we've already done the arithmetic for this thing. Very simple, right? There's the real part. There's the imaginary part. Another way to write it is delta times the absolute value of this thing. Okay? So quantum mechanics is so nice and easy. First order differential equation, time, oh wow, isn't that? It's homecoming week, right? Except we got to do a lot more with that first order than you had to do with the second order, as you'll see as we finish this whole unit here. Okay. In any case, there's going to be a polar form of it that looks like this, with this 1 over the square root of that magnitude L squared. Okay? So just plain old magnitude L is this thing. And this has really nice geometry. This is what the Lorentz-Green's function looks like if you have really high quality and no flat tire that you can see here. That's where the flat tire was, right? We'll look at the flat tire more in plots that come up here. But just for now, I want you to see that this is our dipole function from complex variables. And this is called a Smith plot. So let's catch up on the other screen here and look at some of those with some light on it. This is called the ideal Lorentzian. That's when you talk about a Lorentzian function, del over del squared plus gamma squared, or gamma over del squared plus gamma squared. That's the Lorentzian, but there's its real and imaginary parts should not be separated. Okay. So here's Pythagorean relations. Once again, a Thales geometry. Thales geometry. Okay, it makes us do that funny cycloid stuff that we talked about, get the angles right. Now here, I've got this guy going up here, and what I'm doing is just looking and knowing that's a right angle right there, okay? And this is my rho, that's what I'm doing. And I will always be on a circle. This is giving me the equation of a circle that goes this way. And the other one, the gamma one, is giving me a circle that goes that way. So what we're going to be doing here is looking at the beat period axis. That's the inverse detuning thing, 1 over delta, the detuning, 1 over the delta. And this is going to be the lifetime axis here. Decay rate, inverse decay rate is lifetime. Okay, 1 over gamma versus 1 over your detuning. Okay, those are the two main variables we've been playing with here. Real and imaginary parts of the response function. But now it's really simple. Everything follows a circle, and the Thales circle. Okay. Now, modern instruments, modern digital oscilloscopes and things like that, will take this old function, bunch of circles, orthogonal orthogonal curvilinear coordinate system, an OCC, that's made out of the 1 over z. This is invented by Philip Smith, Smith's chart. Every engineer had to buy a whole stack of these things as they were doing electrical engineering of cables and microwaves and things like this. This is basically when you have a wavy Ohm's laws, you have the voltage, okay, is impedance times the current. And both of these are complex variables, all three of them are complex variables. So doing 1 over z is something you have to do a lot of. That's the Green's function, 1 over z. There's just the impedance. So you take the voltage divided by z, that's your current. That's what you're actually going to be measuring. You want to know what the phase of that is, what the amplitude of that is, and how it compares with the springs of these things. So you'll find these sometimes taped to the front of a digital instrument. It has not died with the digital age. It's kind of an interesting thing of somebody who has long since passed away, and passed away just the year I came to this university. Okay, now, see if there's anything else I need to say here. Oh yes, let's finish up here. Then I want to get started on the two oscillators, but I'd like to finish up here with the construction that's very similar to the construction that I first gave you for ellipses. Remember that construction where you had two circles and you draw a line across the radius and you look where the inner one hit the small circle, and then where the radius, same radius, hit the big circle, and you drew a right triangle underneath that? You do a similar thing here, only you do it with a Thales a thing like that, and you ask, after you've set the B value, that's when we're talking about the most common Lorentz function, okay, which is y equal b over x squared plus b squared. Okay, that's the gamma basically that we're talking about here. Okay, so I set that, and then I make the scale to be just right to have this be 1 over b. Okay, so I'm talking about a b that's, say, less than 1, and then there's the 1 over b. So whatever scale I use to make that, then I will make a Lorentzian. Now this Lorentzian, this comes before Lorentz somewhat. This is 1700s. This is Maria Tina Agnesi. I would introduce you to her. A hot chick. Okay? She really amazing mathematician. Okay? She is in Italy, most of her time in Italy. And this curve, you'll see it in old calculus books and maybe some of the new ones, it's called the witch of Agnesi. It's anything but a witch. But the hat is a witch's hat. Okay, that's why it's called a witch. Mathematicians do this. They give weird names to their curves. Okay? And it's kind of colorful. All right? Anyway, that's what this is. That's what we're constructing here. You just pick, a particular value for a radius. In other words, you pick a particular phase angle, okay, draw it out there, and see where it hits the circle that you drew by doing that, and where it hits the B line, okay, and put a point. Then you move it on, do another right angle, and get another point there. You see, so it's the same sort of, making a little shoe with a heel. Remember, the heel instep, instep and whatever you call the back of the shoe. Okay, heel, sole. Okay, so this is up on a side here and working off of a circle and a straight line. Okay. Common Lorentzian function number 1. Okay, that's the imaginary absorptive part. That's one you get your work out of. Okay, and there's the other one. This one Agnesi knew about, but her name doesn't appear on it. It should. You just turn the whole thing on the side and draw like this. There's your response function, and we mostly were working with minus this thing, where we were going the other way with the, remember that thing that started high and then fell off, right? And then that distance right there corresponded to full width apnexum. Okay? This is x over x squared plus b squared instead of b over x squared plus b squared. Common Lorentzian function 2. This is the refractory part of an optical response. Determines your wave speed. This determines how long your wave is going to last in a damping medium. Here's the constructions that go with that. Now, it might not hurt just to go ahead and look at, and I'm hoping I have a link here that lets us look at the thing. But I would like to show you, and I guess I have to do it on this one because now they're going to be those dark things that don't show up so well on that screen. But here is the geometry of those two circles that we talked about. The Thales geometry for the real, I should say the imaginary part, and then the Thales geometry for the real part that makes this function. So that things on the side instead of straight up. Okay, so that is what you see if you look carefully at this plot that we did, where we had the potential function 1 over z. Remember that guy? That you could write as cosine theta divided by r plus I sine theta divided by r. Real simple little function. That's what we've got here. Okay, and then the field where you take the force field as the derivative without a minus sign of the potential, right? And that's 1 over z squared. So we're plotting the flow lines, that's the blue stuff, remember? And the potential lines, they're all circles. Remember that? And I should say, it doesn't show up that well in this plot, but if you take that dipole function and cut it just off the on the y-axis, the plane, parallel to the x-axis, okay, and the closer you get, that's the more quality of the oscillator. There's the dip that you're seeing here, and then across this way, as you approach the y-axis, you get sharper and sharper, approaching infinity, with the imaginary part of this 1 over z, the Smith sharp. Okay, so this is just tying some loose ends. of our complex variable analysis to really important function, the function that describes response of oscillation. Okay, there's a better picture right there and there of this 3D plot. Okay, see how that comes about? Just that's a cross-section of what we've already looked at in our 3D complex variable plots of the potential. Okay, let's go on both of these to the next subject, which involves oscillators that feed each other resonantly. And to get that, I will open up here on lecture 21. As you can see, we are going a little slower in this class than we usually do, so this makes sense too.
We have a really good batch of students this semester, so it's interesting that we're going slower. I mean, naturally.
Yeah, in some ways we're going fast, in some ways we're going slow. I'd like to take time with these things because it's a matter of appreciating the artistry of and the geometry of the things that we talk about. So here is the key lecture for, oh gosh, did I?
Sort of old.
It's up here.
Yes. Still dated. Yesterday.
Looks good. Let's get rid of the things and get it started. And just give you a feeling for what we're going to be doing next time. And what we're going to be doing next time is playing with the mathematics that deals with that thing over there on the overhead projector. And in the process of doing that, I want to go through my unique, as usual, and favorite development of eigensolutions. But let's just get far enough so that you can see what it is that we need to, why we need to do that, and how it helps. But we're going to be tackling, if we get started on this, and we're really over time now, so I don't think we'll do that. But I want to zip through this part fairly quickly. That's a favorite matrix of mine, and you'll see why it's so favored in the thing. Basically, with coupled oscillators, and it can be two one-dimensional things, like the thing that's sitting on the overhead projector there, and as movies throughout the lecture. Two one-dimensional oscillators sliding on a frictionless wall. That doesn't work so well practically. This seems to be the best practical thing that I've come up with. And or it could be a single mass in 2 dimensions with difference or some kind of coupling springs that make it into a 2-dimensional thing. And we're going to plot all of these things kind of like that, just to get the Lissajous patterns and all that come with this sort of thing. So you all know how to do this already. We've talked about this enough already, so it's a good time to go ahead and just quickly see what it is that's involved. Kinetic energy, half mv squared for both the masses, could be different masses. And then it could be different springs, K1, K2, and then a coupling spring. So that's 3 different springs constants that are here. So there's your potential. Now this is the best way to set up the force equations. You can eyeball it and get the force equation, very often make a sign error. This prevents you from making a sign error because it doesn't matter whether I have x2 minus x1 or vice versa. It's still squared, so it's the same. And when I write that out as a matrix equation, I usually get it right without even with my faulty algebra. That is the thing that we need to solve there. Now, operator notation, we're going to be using very, very powerful notation of matrix. And then it's going to be a question of getting the eigensolutions of a combination of these matrices or each of them individually. That depends on what kind of Green's function you want. I should point out, and this is something I don't want to waste a whole lot of time on, this is written up, this is just, you know, one of my unique interests is trying to restore symmetry where there wasn't any. And the usual thing is that the masses are not equal if we're talking about typical molecules, but yet you can make them sort of equal by just putting a rescaling on this thing. You have to be careful about this thing, but when you get done with it, you'll have a symmetric matrix that has both of the masses in there, sort of the golden mean of the two masses figures underneath a queer kind of K constant that involves the masses as well. So, I say caution is advised since force symmetry may give modes with imaginary frequency. You know that it's not physical. But when it does work, it's kind of neat. In any case, usually what you do is you just take the inverse of this thing and apply it to both sides and end up with an equation that has various k's over m's. And then the idea is to decouple these equations. That is to find special directions where this thing can move without having coupled motion. And what does that mean? Well, we've already talked about quadratic forms. And that's what the potential is for this thing. Okay, no matter what values I have for k's and m's, I can make a potential that looks something like this and plots out something like this with contour lines. And then it's just a matter of finding that magic direction where if you get on that direction so that the force that that thing applies to you, that is, if I'm here, remember, you draw a tangent to that point, then normal to that will be the actual matrix times x. So the force will be not along the distance that you, the position that you were, but over here someplace. So that's the force equal minus the gradient of v. Now we've got our minus sign back again. The minus k dot x that's in the original equation that we talked about just a few minutes ago. Okay? So if I can go up there where that force is directed down the fall line directly, then I just have to figure out what the frequency is for that sort of oscillation, and that will be dependent on having various eigenvalues and eigenvectors. So typically we'll have a beginner's slope, which is lots of distance between the topography lines, not much force, not much frequency. You go slow, but you don't break your ankle. Then there's the advanced slope here where the black diamonds are, and you're really going fast and you do break your ankle. So you have those two choices to run on. And then there's the whole ski resort in between. Okay, we refer to them sort of geographically when we actually get to doing that. So we're going to be working with, basically, you know, I'll end with this. This is the an application that we've already seen, but it is the way we'll plot them. There's the ski bowl right there. Okay, there's a continued fraction of the eigenvalues. That's interesting because that'll tell us what the geometry of that Lissajous pattern is that this thing makes. And you see there already are beats between these two oscillators. And the 90 degrees, you see, this thing is ahead in phase, then it's losing to this one. You see, it's leading it, so that one grows at the expense of that one, just like our driven oscillators was doing. Okay, and then this is just the opposite now. This one is leading that one, and therefore it's giving energy to this one. The sum of the areas of these two circles is a constant. That's the total energy. That's oscillator mechanics in a nutshell. We'll end with that. And we'll start right away next time doing the matrix 1, 2, 3, 4 and get the mathematics out of the way. of projection operators, and some little bit of group theory. Okay? All right. We're not too far over our time limit today, but we'll see you on Thursday. And don't miss the seminar this week. Rick Heller from Harvard. I've already mentioned his artwork, right? When we did the color Lagrangians, okay? I was working with him at that time in Los Alamos. He always gives a good talk, so. And you're all invited on Friday night to dessert. And if you want to come to us to dinner too, you can do that. We're going to go probably to Formosa or else Taste of Thai.
And dessert
So
will
we
be
got
at your place.
And I'll give you a map how to get to my place for the dessert afterwards. He's very personable and he loves to talk to the students, sort of a Feynman-like character.